Welcome to the Deep Dive. Really glad you could join us again. This is our ongoing series exploring the amazing online encyclopedia of integer sequences. It's tailored specifically for you, our number theory students. So today we're diving into a really neat one, OEIS A000255. You might know it as Euler's permutation sequence. And our mission today isn't, just to list numbers. We want to try and uncover the story behind it, the history, some surprising connections, the elegant mathematical structures that pop up. To get us started, think about this. Picture a party, right? Everyone throws their hat in a pile in the middle of the room. They get mixed up, handed back totally at random. Now, here's the captivating question. What's the probability that absolutely no one gets their own hat back? It sounds simple, maybe, but this hat problem, it's actually a classic gateway into understanding something called derangements. And I'm thrilled to be joined today by, a brilliant mind, a Fields Medal-winning mathematician to help us navigate all of this.
That hat problem is, a perfect starting point. It's a classic combinatorial puzzle. And it leads us right into the heart of today's sequence. So our mission, as you said, is pretty clear. We'll first unpack this idea of derangements, and then we'll see exactly how OEIS A000255, Euler's permutation sequence, is, deeply and beautifully connected. It offers some really unique perspectives.
Fantastic. So, to lay the groundwork for A000255, let's start there. Derangements. What exactly are they? How do we even begin to count them?
Absolutely. So at its core, a derangement is just a permutation of a set of items, think numbers, letters, hats, where no single item ends up back in its original position. So in our hat problem, it's exactly the number of ways that nobody gets their own hat. We can look at some small examples. Maybe it helps to make it concrete. We usually use Bn for the number of derangements of n things. So for n1, just one person, one hat. Well, there's no way to derange it, right? The hat has to go back to its owner. So B1 is 0.
Right, makes sense.
For n2, say hats 1, 2. Only way nobody gets their own hat is if they swap 2, 1. So there's just one derangement, B2, 1. For n and 3, hats 1, 2, 3. Now it gets a bit more interesting. The possibilities are 2, 3, 1, and 3, 1, 2. Those are the only two where no number is in its original spot. So B3, 2.
I see the pattern starting.
Yeah, and it goes quickly. B4 is 9, B5 is 44, B6 jumps to 265. These numbers are actually famous in their own right, sometimes called subfactorials or uncontrunture numbers. And you can find them listed in the OEIS as A000166.
Wow, 44 derangements for just 5 items. That's quite a leap.
Yeah.
So is there a formula? How do we calculate these without listing them all out?
There is, and what's fascinating is how elegantly they're generated. We can compute Bn using a really neat recurrence relation. Bn1 plus Bn2. This works for n greater than or equal to 3, and you just need those base cases we found, B1, 0 and B2, 1.
Okay, Bn1 plus Bn2. That looks interesting. Is there an intuitive way to understand why that formula works?
Yes, absolutely. There's a nice combinatorial argument. Let's think about our n people and their hats again. Pick one person. Let's call her Alice. Alice definitely doesn't get her own hat back in a derangement, so she must receive someone else's hat. There are n1 choices for whose hat she gets. Let's just say she gets Bob's hat.
Okay, Alice gets Bob's hat.
Right. Now, we have to consider Bob. Two things could happen with Bob. Case 1, Bob gets Alice's hat. So Alice and Bob just swap hats. They've taken care of each other. Now, the remaining n2 people also need to be deranged. None of them can get their own hat. The number of ways to do that is Bn2. And since there were n1 initial choices for whose hat Alice could have taken, Bob's, Carol's, etc., this whole case accounts for n1 Bn2 possibilities.
I follow. Alice picks one of n1 hats, say Bob's. If Bob takes Alice's, the rest must be deranged. Makes sense.
Exactly. Now, case 2. Bob does not get Alice's hat. This is slightly trickier. Think of it like this. Bob still needs a hat, but it can't be his own, and it can't be Alice's since Alice already has Bob's. It's kind of like we temporarily pretend Bob's original hat is Alice's hat for the purpose of this step. We now have n1 people, everyone except Alice, and n1 hats, all except Bob's original hat, which Alice has. We need to arrange these n1 items so no one gets their assigned hat, including Bob not getting the hat we've labeled as Alice's. This situation perfectly matches the definition of Bn1 derangements for n1 items.
Ah, okay. So we're essentially forcing a derangement on the remaining n1 people, treating Bob as if his forbidden hat is Alice's.
Precisely. And again, since Alice had n1 initial choices for whose hat to take, this case contributes n1 Bn1 possibilities. You add those two cases together, case 1 and case 2, and you get n1 Bn2 plus n1 Bn1, which is exactly n1 Bn1 plus Bn2. That's the recurrence.
That's a really clear explanation. Thank you.
And what's also quite remarkable, there's another simpler looking recurrence relation. Bn bm-1 plus neg1n. Also for n dash.
No, nbn1 plus next 1n. That looks very different. How did that come about?
It arises from a slightly different way of thinking about building the derangements, often involving the principle of inclusion-exclusion, actually.
You mentioned inclusion-exclusion earlier. That's the more general method.
Exactly. Inclusion-exclusion is really the bedrock principle here. It lets you derive the explicit formula for derangements, which is bnn times the sum, 10 Mike 11 plus 12, 13 plus n plus minus 1nn.
Okay, that's the full formula. N times that alternating sum of inverse factorials.
Yes, and this formula leads directly to that fascinating probability result we touched on. If you calculate the probability of a derangement, Pn, this is Bnn, you just get that sum. 10, 11 plus plus, negative 1, n. As n gets large, this sum is the Taylor series expansion for 1n, so the probability converges to 1e.
Which is about 0.368, or 36.8%. So for a large party, the chance that nobody gets their own hat back stabilizes around 37%. That's still kind of mind-bending to me.
It is, isn't it? A fundamental constant emerging from such a simple setup.
Okay, so that's derangements, A000166. Now let's bring in the star of today's show, A000255, Euler's permutation sequence. Let me list the first few terms again. A01, A1, A23, A3, ALN, plus N1, A5, 309. Clearly different numbers. And you mentioned its recurrence is AN, AN1, plus N1, AN2. Similar structure to the first arrangement one, but slightly different coefficients. So what are these numbers counting? What's the story here?
Right, that's the key question. What combinatorial object corresponds to AN? Well, one important interpretation, which goes back to Euler himself, is that AN counts the number of permutations of n plus 2 elements that have no fixed points, so they are derangements, and they also start with the element 2.
Okay, wait. Derangements of n plus 2 things, specifically starting with 2.
Exactly. So for example, let's take n2. The sequence value is A2. This means there are 3 derangements of the set 1, 2, 3, 4 that begin with 2, and those are precisely 2, 1, 4, 3, 23, 41, and 2, 4, 13. If you check, none of the numbers are in their original positions. 1 is in first, 2 is in second, etc., and they all start with 2.
I see. That's a very specific condition, starting with 2.
It is,
Yeah.
And it connects to something called Euler's difference table, which is a way of organizing information about permutations. A000255 actually appears as the second column in a specific version of this table. It signifies its importance in that combinatorial framework. But perhaps the most revealing thing is how A000255 relates back to the derangement numbers, A000166. There are actually 2 very neat connections.
Oh, okay.
First, there's a simple additive relationship. AN is just the sum of 2 consecutive derangement numbers, specifically AN, A00000166, plus A00000166, 3. So 1 plus 2 equals 3. It works. It does. It holds generally. So Euler's sequence term is built directly from 2 adjacent derangement terms. And second, there's a multiplicative relationship, which maybe tells an even deeper story. It turns out that A000166, n plus 2 equals n plus 1, AN.
A000166, n plus 2 equals n plus 1, AN. What does that mean combinatorially?
It means that if you look at all the derangements of n plus 2 items, you can actually divide them perfectly into n plus 1 equal size groups. And the size of each of those groups is exactly AN. Remember A311? This formula says A000166 3 plus 2, which is A00001665, or B5 should be 3 plus 1 A3. That's 411, which is 44. And indeed, we saw earlier that B5, 44.
Wow. Okay, so AN represents the size of these fundamental blocks when you partition the derangements of n plus 2 items.
That's a great way to put it. It's like AN is a fundamental building block or structural constant for derangements of a slightly larger set. So these 2 sequences, A000166 and A000355, they're distinct, but they're incredibly intertwined. They just reveal different complementary aspects of permutations without fixed points.
That's fascinating. The connection is much deeper than just having similar-looking recurrences. So bringing this back to you, the learner listening, what are the takeaways here? Beyond the mathematical elegance, are there practical implications or applications? Let's revisit that Yankee Stadium idea. 54,000 odd people randomly assigned seats. We know the chance of no one getting their assigned seat is about 1m. But what about the chance that at least one person ends up in the right seat? That's the complement, right?
Wow.
1 probability of derangement.
Exactly.
And we looked at that table earlier for small numbers of seats. 1 seat, probability of match is 1.2 seats, probability is 0.5. 3 seats, it goes up to about 0.667. 4 seats, drops back down to 0.625. 5 seats, up again to about 0.633. It oscillates. But you said it converges?
It does. It converges. And just like the probability of a derangement converges to 1A, the probability of at least one match converges to 1A.
Which is about 0.632, or 63.2%.
Precisely. So even in that huge stadium, the probability that at least one person finds themselves in their originally assigned seat is about 63%. It doesn't go to 100%, it doesn't go to 0%, it settles very quickly around the specific value related to E.
That oscillation and convergence is so striking. It really challenges intuition about large numbers and randomness.
It really does. And it highlights the power of asymptotic analysis in combinatorics. It shows us why studying these sequences isn't just, a theoretical exercise. And from a computational viewpoint, calculating these numbers efficiently, the BNs and the ANS is a great example of where techniques like dynamic programming come in really handy.
Dynamic programming, using the recurrences but storing results.
Exactly. Instead of recomputing values over and over in a purely recursive way, you can use memoization storing results as you compute them, or build the values iteratively from the base cases upwards. These are fundamental techniques in computer science for optimizing problems with overlapping subproblems, which is exactly what we have with these recurrence relations.
So understanding the recurrences isn't just for theory, it directly informs efficient computation.
Absolutely. And the reach of these ideas extends further. We mentioned Euler's difference tables. These concepts generalize to more complex mathematical structures like certain symmetry groups studied in advanced algebra, things called complex reflection groups or hyperoctahedral groups. There are even connections, believe it or not, in theoretical physics related to analyzing particle interactions like quark and gluon diagrams where permutation structures play a role, and maybe more down to earth in areas like cryptography or statistical analysis of experiments. That simple hat problem truly opens doors to some very sophisticated math.
It's incredible how far the ripples spread from that one initial question. So today we really dove deep into OEIS A000255, Euler's permutation sequence. We saw how it's not just an isolated sequence, but deeply structurally related to derangements A000166. We went from the hat problem to recurrence relations, the principle of inclusion-exclusion, and that really surprising convergence involving the number E. I think it's just a fantastic reminder that mathematics finds these amazing patterns and connections, often in places where our everyday intuition might not expect them at all. We really hope this exploration has given you, our listeners, not just some new facts, but maybe a fresh appreciation for the intricate beauty woven into the world of integer sequences.
And maybe something to ponder as you continue your studies in number theory or related fields. Think about what other everyday situations, maybe things you encounter randomly, might secretly be governed by sequences like these ones that oscillate, that converge in unexpected ways. And perhaps consider how the methods we touched on, combinatorial reasoning, recurrence relations, dynamic programming, how these tools might help you identify and analyze those hidden patterns. The landscape of mathematics is truly vast, and there's always another fascinating path waiting to be explored. Thank you for joining us on this deep dive today.